All right, let's do a review for the final exam. If you go to the web page at the bottom, you'll find an example or the old exam from spring 2019. It's somewhere down here, way at the bottom, old final right there. So if you pull that up and open it up, what we will do is we'll run through that. Not everything on that exam is pertinent to us. We didn't do some of the material. We did other sorts of things, so we're going to use that as just a starting point. The first exam covered all of the introductory material all the way through the life histories. So what we want to do for this final exam is talk about demography, competition, predation, community structure, and a little bit on optimal foraging. So we need to be able to understand those phase planes in competition. We need to talk about stable limit cycles and that sort of stuff. So follow along on this first exam, and let's see what we can get done. So I've already opened up that exam. Here it is. The first question that pops up is about functional responses and numerical responses. So if you go to the lecture on predation, there we have it. There's that slide. A functional response is defined as prey density increases, each predator can consume more prey, versus a numerical response, as prey density increases, predators increase in number, and that larger number of predators consumes more prey. All right, so here a functional response is as prey density increases, each predator can consume more prey. So that is the correct answer. Question number one, the correct answer is A. Next, for number two, consider the figure below. This figure illustrates that Sorex has a large numerical response to increase prey density, while Peromyscus and Blorina had a small numerical response to increase prey density. Well, if you look at it, right, Sorex does have a numerical response. It increases steeply here, so that would be a true statement, right? Peromyscus and Blorina appear to have a functional response rather than a numerical response. Question number three. In a coevolutionary system, an increase in fitness for one species results in a decrease in fitness for the other species. That is true. Think about coyotes and bunnies. As bunnies run faster, right, their fitness increases because they escape predation by the coyotes. But as they run faster and escape predation by the coyotes are at now a disadvantage, right? So their fitness decreases, at least temporarily. So question three is true. Question four, consider the two equations below. Which of these represents the equation for the predator population? Okay, well, P for predator, H for herbivore. Okay, that's one clue. But recall what happens with the predator. The predator increases, its population grows as a consequence of its interactions with the herbivore, right? And without any herbivores to feed on, it's simply going to experience a death process. So this upper one here is for the predator. This is for the herbivore right here. So the herbivore population grows with R, right? That's the growth rate of the herbivore population. So that's just that exponential growth. And then its population size is reduced by PHP. Remember, we talked about the Brownian motion model for predator-prey interactions. So you can model how many interactions there are by simply multiplying the number of herbivores times the number of predators, and then some proportion of those result in a kill of the herbivore. So the correct answer for the predator is A. B is the herbivore. All right. For the equations in question 4, what does the term A refer to? So here we have A. P shows up here and here, so that's the proportion of the interactions that result in a kill. So A is going to be some kind of assimilation efficiency. Hey, that's easy. A for assimilation. Makes perfect sense, right? So A is for the assimilation efficiency. All right, question 6. For the equations in question 4, what does the term P refer to? It's not birth rate, it's not death rate, it's the proportion killed or the portion killed. Okay, we've already done assimilation efficiency. Death rate is D, birth rate is going to be B, right? Growth rate will be R. Niche overlap is going to be alpha, so it's going to be the portion killed. Oftentimes on multiple choice questions, two things. First of all, to improve your probability of getting the right answer, eliminate the ones you know are false. Secondly, your gut instinct, your first response is usually, not always, but usually the correct one. All right, so for question 6, P refers to the portion killed, C. All right, question 7. Use the figure above to answer this question. If prey consumption is logistic with respect to prey density, then the functional response is what? Okay, so a type 1 functional response is linear. A type 2 functional response is asymptotic. The logistic functional response is this one. Think about logistic population growth that produces exactly this kind of a curve. Okay, so logistic with respect to prey density, then the functional response is a type 3 functional response. So the correct answer for 7 is C. 8. True, false. Only the type 3 functional response is density dependent in a way that promotes population regulation. That is a true statement. Recall, the low values here on the type 3 functional response are a consequence of prey refugia or the predator not having the right, it's not prey refugia, but it's the predator not having the right search image. And then up here, it's a consequence of prey refugia. Okay, so the correct answer for 8 is true. The correct answer for 9, the type 3 functional response, is the one most likely to regulate prey populations. That is true. Okay, what can cause a type 3 functional response? Well, we just went over that. A, factors that cause low hunting efficiency at low prey density. That's true. B, failure to develop an appropriate search image without positive reinforcement. That's true. C, presence of prey refugia at low densities. That is true. So the correct answer for 10 is going to be D, all of the above. All right, so now perform the phase plane analysis on the figure below and indicate whether the system is stable or not. Well, clearly this isn't going to happen in a jot form exam, but you should. So the answer to the question is you may have to do the phase plane analysis, but you're not going to draw it on the exam. So the question is going to be, is this one going to result in stability, or is it going to result in something that cycles out of control? Okay. So let's think about that. Let me see if I can pull up if I even had that on a slide. Remember this diagram, this diagram here is a little bit different from this one, right? In this one, you notice the prey isocline is horizontal and the predator isocline is totally vertical, and that results in these stable limit cycles, like a lynx snowshoe hare cycle or a fox lemming cycle, okay? But here, this one is off to one side, right? So the prey isocline drops down here and it drops down like that. And then the predator isocline is bent on this side, okay? So what happens under those circumstances? Well, if you'll recall, the alternative circumstance was this one where the predator isocline was to the left of the hump, right? Then you had a system that cycled to extinction. The alternative with this one, when this one is off to one side, is that it's going to cycle back into the stable point. So in this scenario, if you perturb it from the equilibrium point, it's going to cycle, but then it's going to cycle back in towards stability. Okay? So this one will be a stable limit cycle. It is going to cycle in back towards the equilibrium point. All right. Question number 12. Consider the graph below. If predator densities are high, then A, the evolutionary response on the part of the prey should be low. Okay, let's see what's going on here. On the x-axis, rate of exploitation. Okay, so the relative effectiveness of the predator and prey adaptations. And this is rate of evolution. So as the rate of exploitation is higher, okay, in other words, as more and more and more prey are being taken, the selection pressure on the prey is intense, then the rate of evolution for the prey should be high. But if the rate of exploitation of prey is high, the predators are doing something right, okay? They're having good success, there's no reason to change anything, their rate of evolution is going to be low. When the rate of exploitation is low, in other words, the predators aren't very good at getting the prey are essentially being left alone. There is no real strong selection pressure on them, so their rate of evolution will be slow. For the predator, their ability to exploit the prey is low, so selection pressure on them is going to be high. All right? So if predator densities are high, then the rate of prey exploitation is going to be high, okay? And the rate of evolution on the part of the prey should be high. So A is incorrect. So B would be a correct answer because evolutionary response on the part of the prey should be high. Evolutionary response on the part of the predator should be low. That's also true. D, evolutionary response on the part of the predator should be high. No. So for question 12, both B and C are correct answers. On your exam, I will do my darndest to make sure that if there are two correct answers, you know that. Okay? I think what I will try to do is make sure that there is only one possible correct answer for each question. If not, I will indicate that. If I screw up, then I will accept multiple answers. All right, question 13. Consider a system in which there are two predators. For example, bats might take an insect when it flies, and shrews may take the insect when it lands on the ground. From an evolutionary perspective, what problem does that pose? Well, the problem is simply going to be that there are different selection pressures acting on the prey species. Any adaptations to minimize predation by one predator might exacerbate the situation with the other predator. Okay? So the correct answer is going to be C. The possible evolutionary responses may be constrained by the differing selective regimes imposed by each predator. The correct answer for 13 is number C. Which of the following is not one of our hypotheses for community species diversity? We've gone through all of these. This should be pretty straightforward. We talked about competition, predation, primary production, not global warming, right? I mean, that's not one of our hypotheses for community species diversity. Stability of primary production, evolutionary time, ecological time, habitat diversity, climatic stability, all of those things are true except for D. So 14, the correct answer is D. 15, true or false? In an ecological sense, predation and herbivory are just different levels of the same phenomena. The critical difference is that predation terminates future fecundity, while herbivory generally reduces it. That is a true statement. 16. Adaptations to avoid predation include hard shells or spines. Yeah, that would work. Turtles and porcupines don't get preyed upon a lot. Expanded auditory bullae. That's true because kangaroo rats have these gigantic auditory bullae. You recall that from the one slide. And they're able to hear snake farts at 1,000 yards. So that's a good anti-predator device. Poison glands in the skin. Yeah, that's what toads do. Saltatorial locomotion, hopping. That's what kangaroo rats do. That works. Herding behavior. There we go. Herding behavior. Yes, there's safety in numbers. If you're in the middle of the herd, your chances of getting taken by the wolf are reduced. And then behavioral displays. Okay. Sure, when baboons bare their canines, it gives the predator pause, and sometimes that enables the baboon to get away. Right, so all of those are adaptations to avoid predation. So all of these should have been circled on this question. Okay, for your exam, I would have then a statement that says all of the above or something of that sort. All right, 17, true, false. Amongst foragers, we can identify two basic types, time minimizers and energy maximizers. Yes, we did that. Okay. 18, if you were standing at the base of the Sierra Nevada mountains in Southern California and you wanted to be in the Ponderosa pine forest, which direction would you travel? Well, there are two things you can do. You can go upslope, so you can go to higher elevations where it's going to be cooler, or you can go north where it's going to be cooler. Okay, so either up in elevation or north. Okay, so the correct answer is going to be E. 19. What determines the distribution of Ponderosa pine? All right, well, this is actually from the previous exam. So from the first part of the semester. So we don't have to worry about question 19. We don't have to worry about question 20. We did very briefly talk about question 21. So it is a fact that as biological systems become less diverse, they become less stable. Currently, humans and their agricultural beasts, cows, pigs, horses, make up about 95% of the mammalian biomass. Chickens make up 80% of the avian biomass. Is this current distribution of biomass sustainable? Well, let's see. A, yes, as long as we can control rates of predation. No, that's silly. B, yes, as long as we maintain at least 5% of the land area for national parks. No, that's not going to be enough. C, no, the system is susceptible to perturbations from equilibrium. Or D, no, the system is self-correcting and will persist. The only question is, for us, is if humans persist as well. The correct answer for 21 would be either C or D. Okay. Recall when we had our discussion of food webs and food chains, right? Stability of the system was dependent on the connectivity of the system, how many links there were in the system. The fewer links there are, the less stable it is. The human system, as we've structured it now, there are relatively few links. So the system is not particularly stable. So that presents a problem for us as climate changes, because climate change will reduce the stability of the system even further. So the question is, are we going to still be there after the system returns to equilibrium or not? Okay, you should be able to solve this little optimal foraging equation, right? E is energy, right? T is time. Lambda is the encounter rate. H is the handling time. All of those things are filled in on here. Practice and try and solve this equation. Remember, what you need to do here is the following. It's asking you should the predator be a generalist or a specialist? In other words, should it take only one food item? And if so, which one? Or should it take both food items? So the way to solve this is to first solve it for both food items. So just use these numbers and plug them into this equation up here. E1 is going to be 50, E2 is going to be 100. So just plug the rest of these values into that equation and solve it. You're free to use a calculator. Then assume that E2 and H2 are 0, right? So just remove that part of the equation and solve the equation just for prey item 1 and compute the number. Then solve the equation a third time just for prey item 2. So assume that E2 and H1 and lambda 1 are 0 and just solve for food item 2 and compute that number. Whichever of those numbers is largest will tell you whether the animal should specialize on prey item 2, prey item 1, or whether it should take both prey items. Okay? All right. Then this is our marginal value theorem, right? We use this in the development of our ideas for the giving up density study that you guys did. T sub t, that's the travel time to the foraging patch. T sub p is the patch occupancy time. And when you should leave, that's determined by the point that you start traveling to the patch, and then you draw the tangent line to that economic return curve like that, and where that tangent intersects, that's going to determine your patch occupancy time. Notice what happens. If the travel time to the patch is short, you should leave the patch earlier. If the travel time to the patch is long, you should stay longer. Of course, we could change this and change the rate of return here so that it's shallower. And you could imagine then that if the return is shallower, then you should leave the patch earlier as well. All right. Question 24. As the rate of exploitation by the predator increases, the rate of evolution on the part of the prey species increases. That's a true statement. While the rate of evolution on the part of the predator decreases. That is a true statement. So 24 is true. 25. Communities are evolutionary units. We had some discussion about that. The correct answer there is C. That has not yet been determined in most cases. Okay, let's scroll down here and see if yes. All right, recall this diagram right here. We used this diagram in our lecture. If you look at this top diagram, if these curves here are the resource utilization curves, or the niches for individual species in a community, you notice that all of these species clump together, all of these species clump together, all of these species clump together, and all of these species clump together. There's a little bit of overlap, but for the most part, the species clump together. So in this top diagram, it's fair to say that these communities are co-evolved units. In the diagram below, notice that the species niches are just all over the place. They don't clump into nice groupings like that. So in this example, the species are independent of the communities. So in this one down here, they are not co-evolved units. The species are independent and they just show up in a community and they either make it there or they don't. All right. If communities are co-evolved units, then we infer that communities replace each other as units. That would be a true statement. Notice it says if communities are co-evolved. So that would be true. 27. Consider the following communities: Ponderosa pine woodland, pinyon juniper woodland, creosote scrub, sagebrush scrub, Mojave desert. Now, I recognize that you guys don't have any real familiarity with those communities, but we have talked about them. Okay, these are examples of communities as evolutionary units. Probably not. They are examples of Merriam's life zones. We did talk briefly, at least, about Seahart-Merriam. Okay, they are not random assemblages of species. They are assemblages of independent species to some degree. So the correct answers for question 27 would be either D or B. Okay, so they're examples of Merriam's life zones, and they are assemblages of independent species. All right, we just did this one right here. So the top figure indicates A, co-evolved communities, while the bottom figure indicates random assemblages of species or tolerance limits to the local physiognomy. Okay, so A for the first one, and then either B or D for the second one. All right, does the sharp demarcation between coniferous and deciduous forests indicate communities as co-evolved units or as spatial units? All right, let's think about that. The sharp demarcation between coniferous and deciduous forests. So, for example, if you were in the Appalachians and you were going upslope, there's a pretty distinct line. It's not a perfect line, but there is this sort of demarcation point, right? There will be a small ecotone between them. Are they co-evolved units? Probably not. Are they spatial units? Yeah. What's happening is that the tolerance limits for the species are fundamentally different. And one of the things that's happening in the Appalachians is that as the climate is changing, the lower elevation conifers are dying back, and the hardwood deciduous forests are moving upslope. So the amount of acreage for coniferous forest is decreasing. So they are spatial units for 29. So 29 is B. 30. As you travel north in the Sierra Mountains, the elevation at which Ponderosa pine community begins becomes higher and higher. No, as you go north, right, the Ponderosa is going to come lower and lower. Remember, the Ponderosa is responding to temperature and moisture. As you go north, it gets cooler and wetter. So the elevation at which you find Ponderosa pine gets lower. All right. So the correct answer for 30 is false. 31. The evolutionary history of each species in a community is essentially independent of other species in the community. For the most part, that is true. There are only a few examples where that is not true. So 31 is true. 32. The distribution of plant species is more strongly correlated with environmental gradients than with the distribution of other species. For the most part, that is true. There are examples where that's not true, but in general, 32 is true. Consider the phase plane given below. Indicate the equilibrium points if they exist. If an equilibrium point exists, indicate whether it is stable. All right. We had talked about this one. Let's pull this back again. There, that's exactly that scenario. Okay, and it depends on which side you're on, right? So this is one. If the perturbation is relatively narrow, you're going to stay in this range right here. If you go too much over here, it's going to cycle to extinction. If you go a little bit over here, it's going to be stable. So the only issue is if we go too far over here, it's going to become unstable. All right, let's now go back to patterns of species diversity, island biogeography. And we had this equation, and this was from the MacArthur-Wilson Island Biogeography work. Notice this equation. If you were to take the logarithm of both sides, and you'll notice here that this is a log scale, and this is a log scale. Okay, so if you take the logarithm of this, it becomes the equation of a line. Okay, so that equation illustrates a linear relationship between area and species richness. S is species richness, A is area, and then C and Z are simply going to be the parameters of the line. So question 34 is true. Here is that line. Okay. So 435, the graph indicates that as islands get larger, they support more species. Yeah, here it's bigger going this way, and number of species is going up. Cuba and Hispaniola have more species than Saba and Montserrat and Redonda. Okay, so that is a true statement. 36. When sampling the species in a community, it is typical that A, most species are relatively common and a few are rare. A few species are relatively common and many are rare. There is always one common species and the rest are rare, or all species are rare. No, a few species are going to be relatively common and many are rare. Think about the birds that are coming to your feeder. You'll have cardinals, and you'll have wrens and chickadees, depending on what you're putting in your bird feeder. Every now and then, you'll get a grosbeak or a bunting or something of that sort. But there are going to be a few species that are common, and many of them are going to be rare. So the correct answer for 36 is going to be B. 37. The distribution of plant species is more strongly correlated with environmental gradients than with the distribution of other species. That's true. 38. How does interspecific competition increase species diversity? My favorite answer is magic, but that's the wrong answer. Okay. So if you think about it, competition is going to natural selection should operate to minimize the amount of overlap between species. Therefore, the niches are narrower, and you can therefore squeeze more species into the community. Okay, so it doesn't increase niche breadth, it reduces niche breadth, thus enabling tighter species packing. Okay, the other possible answer is that interspecific competition reduces population size, thus allowing each species. No, that's actually what happens as a consequence of predation, not what happens as a consequence of competition. So the correct answer for 38 is E, reduces niche breadth. Natural selection is working against species that are overlapping, or against individuals that overlap, right? So it's going to reduce niche breadth and thus enable tighter species packing. How does predation increase species diversity? There, the correct answer is reduces population size, thus allowing each species to be more specialized and therefore reducing niche overlap. So the correct answer for 39 is B. All right, for the next few questions, recall our brief discussion of climate change. Since the late 1880s, annual temperature anomalies have been primarily negative. That's false. You'll recall from the lecture, from the video lecture, it's positive. Okay. Since the mid-20th century, levels of atmospheric CO2 have increased dramatically. That is a true statement. One interesting side note, and we didn't talk about this in the lecture, is that one of the easiest ways to reduce atmospheric CO2 is to raise the price of gas. It's that easy. As you increase the price of gas, people drive less and or they buy cars that are fuel efficient. When gas is cheap, people drive more and they tend to buy big SUVs and things of that sort. So it's a pretty simple solution to the problem. Obviously, it's not a popular solution, but then dealing with climate change is not popular in general. All right, and unfortunately, you know what's happened to the price of gas recently, and for people that do have jobs and that still have money, you'll notice that lots of people are buying big F-150, 250, 350 pickups. They're buying giant SUVs and Cadillac Escalades and things of that sort because gas is so cheap. When the price of gas goes up, and ultimately it will, people will be scrambling for economy cars like Priuses and Honda Fits and things of that sort. All right, question 42. Consider the graph below. On the graph, indicate and label the equilibrium number of species for a large island that is far from the mainland and a large island that is near to the mainland. Okay, so these are near islands, okay, and these are far islands. So far, near, okay, small, large. So number of species, and this is the rate, okay, either number of species per unit time. So here we have immigration on these over here, and we have extinction over here. Well, this makes sense because a small island is going to have greater extinction than a large island, simply because the populations are bigger, right, and the amount of genetic diversity is greater. On a near island, it's an easier target to get to, right, than a far island. So the immigration rate for a near island will be greater than the immigration rate for a far island. So let's now answer the question. For a large island that is far from the mainland, okay, so we want a large island that is far from the mainland, okay, so that's going to be down here, right, large island far from the mainland. That's going to be closer to the mainland as we go up like that, okay? So large island, far from the mainland. Equilibrium number of species for a large island that is far from the mainland and a large island that is near to the mainland. So large island, far from the mainland, and near to the mainland. So large island near to the mainland right there. Large island far from the mainland right here. Okay, so the equilibrium species for a far island that is large is going to be right there. And the equilibrium number of species for a large island that is near is going to be right here. Okay. All right, we're not going to do the ANOVA stuff. You've battled that sufficiently in your giving up density stuff. We're going to skip all of that. We're going to skip all of that. All right, question 49. There is a very strong positive relationship between global temperature anomalies and atmospheric CO2. That is a true statement. 50, increasing the cost of gasoline reduces the amount of CO2 that enters the atmosphere. That also is a true statement. All right, that's a quick run through on that sample midterm exam. I would encourage you to print this out and answer the questions and keep this by your side as you prepare to take the final. Good deal. Talk to you guys later.